you. So we'll have 3 20-minute talks during this next block. Our first one will be from Daniel Hast, and they're going to be telling us about explicit two-cover descent for genus two-cover.
Hi, is the mic working? Is it good?
Yeah.
Okay, great. So first off, thanks so much to the organizers for giving me this opportunity to speak and for putting together this conference. It's been awesome so far. I'm really looking forward to the rest of it too. So what I'm going to tell you about today is some sort of combination number theoretic and geometric picture involving some recent work of mine with basically making two-cover descent and some associated stuff for computing rational points on genus 2 curves, really explicit to the point of being able to run as algorithms and then running those algorithms on a big data set and then seeing, well, how often do these methods work? When they don't work, what's causing them not to work? And so what does that mean for the future of being able to compute rational points on lots of genus 2 curves in practice? And so just to start out, here's our sort of very familiar general problem setup in arithmetic geometry. So we have a smooth projective curve of genus at least 2 over a number field, and Faulting's theorem tells us it has finitely many rational points. But the huge open problem in arithmetic geometry is, well, given this curve, how do we actually compute the set of rational points? It's some finite set. We can start searching, maybe just by brute force, maybe by some more clever method. But how do we know when we've actually found all the points? And this actually sort of breaks down into 2 separate problems, one part of which is, well, how do we know there is at least one point? And the second part is, if we know there's at least one point, or maybe at least a few, how do we know when we found all of them? I'm not going to talk about the first problem. All the curves in question here we already know have at least one point and typically at least a few. And so even in the sort of first case of genus 2 curves over the rational numbers, and so a genus 2 curve is given by an equation of the form y squared equals a degree 6 polynomial in x. So even here, no general method is known. And so for the rest of the talk, we're just going to work over the rationals. So one approach to this problem that actually was the biggest step toward proving what's now Faulting's theorem back when it was the Mordell conjecture, before Faulting's proved it in general, is Chabot's method, which works on the Jacobian. And the idea is basically you fix a prime p, and then you look inside this commutative diagram, you consider the p-adic points of the curve as like this p-adic curve sitting inside the p-adic points of the Jacobian, which is this g-dimensional abelian variety. And then you consider the intersection of that with, well, you can take the p-adic closure of the set of rational points of the Jacobian. And what Chabot proved is if the rank is less than the genus, then in fact this intersection is finite, and therefore this proves finiteness of rational points on the curve. Just to give a sense of why this is true, the key idea is that the rank is actually an upper bound on the dimension of this space here, the closure of J of Q, the dimension as a p-adic manifold. And so if rank is less than genus, this is a proper p-adic submanifold. And so intuitively, just going by dimension, you would expect that the intersection of a p-adic curve with a proper p-adic submanifold is finite. Chabot showed, in fact, that is the case. So Coleman in 1985 refined this, and that's why Chabot's method isn't just of historical interest. And so what Coleman did is use p-adic integration and the theory of Newton polygons to actually extract explicit bounds from Chabot's method. For example, if p is not too small and is a prime of good reduction for the curve, you get this very nice bound that is very often either sharp or close to sharp. Much better than the bounds that you can extract by for example, Falting's or Voita's general methods. And in many cases, this method can actually be turned into an algorithm for computing the set of rational points. And so, for example, Brown and Stoll have implemented this in Magma for curves of genus 2 and rank 0 or 1. And I believe there's some implementation for higher genus hyperelliptic curves. The obstacle there is actually the lack of an implementation of computing the Mordell-Weil group in those cases. But yeah, so this is something that can be made algorithmic. So now let's talk about big data sets of genus 2 curves. Booker, Seisling, Sutherland, Voigt, and Yasaki computed what should be heuristically near complete. Like heuristically, there should probably be a few missing ones, though none are known. But this database of 66,000 something genus 2 curves over Q that have absolute discriminant less than or equal to 1 million. And so this is in the LMFDB, which if you don't know about the LMFDB, go to lmfdb.org, check it out. It's a really cool extensive database of all sorts of number theoretic data, L functions, modular forms, elliptic curves, higher genus curves, Galois groups. More is being added to it all the time. And these objects are also linked to each other when they're related. For example, you can go to the page for an elliptic curve, and then it links to the page for its modular form. So it's pretty great. And there's lots of pre-computed data in there, including rational points. Now, for the genus 2 curves of rank 0 or 1, this list has been proven complete using some variant on Chabot's method. But for the higher rank ones in the data set, it just says known rational points. And this is because it hasn't been proven for those curves. So we'd like to fill that out and make that proven for as many as possible. So this is like the sort of, applied side of the whole Chabot-Coleman theory here. Let's actually do it for this big data set of curves. So what's the issue with higher rank curves? Well, the issue is that if the rank is at least as big as the genus, then this may not be a proper p-adic submanifold at all. And then Chabot's method gives no information. So in this case, there's several things we can do to try to get around this problem. One thing is, well, let's suppose that the Jacobian is not simple, that we have some factor, and then we can pass to the quotient of this, and if it happens that the rank of this quotient abelian variety is less than its dimension, then you can essentially do just a variant of Chabot's method, but you use this map from the curve to this smaller abelian variety in place of Abel-Jacobi. And one example of this, that's probably the most commonly used application of this idea, is, well, if this is a restriction of scalars of an elliptic curve, or equivalently, if you have a map from your curve to an elliptic curve defined over some extension of your base field, then this is called elliptic Chabot, and this is also implemented in Magma. And so this gives you a sort of an alternate method where sometimes you can run Chabot's method by finding like an appropriate quotient abelian variety. Another approach, and this line here has like more content in it than just about anything else in this talk combined. It's aligning over a lot here, but there's this method due to Mignon Kim called non-abelian Chabot that replaces the Jacobian with a larger non-abelian object coming from a bigger piece of the fundamental group. In many cases where the rank is equal to the genus, this is something called quadratic Chabot, or the first non-abelian step here, and this is a very active area of study. There's some implementations there. I'm currently working on another project that involves this. But yes, there's a lot to say about this, which I won't say in this talk. But there is some possibility for going beyond rank less than genus using these sort of non-abelian ideas. Another idea is you can use descent. And the idea of this is use covering collections. So find some covers of your curve and use those to sort of, and then maybe take some quotients of those. And so then you have a correspondence between curves. And the idea is that you might use this to reduce the problem to finding rational points on some finite list of hopefully easier curves. And so this is the main approach that we discuss here in combination with elliptic Chabot-T. So what is descent? And more specifically, what is two-cover descent? Well, the multiplication by m map, this is a degree m to the 2g Galois covering of the Jacobian by itself, right? And now if we think of the curve as a subvariety of the Jacobian by the Abel-Jacobi map based at some rational point, well, now we can take the pre-image of the curve under multiplication by m and get a new curve that's a degree m to the 2g Étale covering of our curve. And this is the source of many Étale coverings of curves, right? Is essentially another way of thinking of it is these are the covering spaces that come from the abelianization of the fundamental group, which is closely related to the Jacobian. And now one can compute a finite set of twists of this curve together with maps to the curve. So a finite set of twists of this covering map such that the rational points of the curve all come from rational points of one of these covering spaces, one of these twists. And so now this reduces this problem of finding rational points on the curve to finding rational points on each of these other curves. And if we're lucky, or if we've constructed things well, hopefully that'll be easier. So that's the idea. And now in our case, genus and m are both 2. And so here, this is a genus 17 curve, which is a maximal unramified abelian 2 covering of our curve here. And let's consider the Jacobian of this. It turns out the Jacobian of this is isogenous over Q bar to the Jacobian of the original curve times a product of 15 elliptic curves. And so you can get this just by looking at Riemann-Hurwitz and seeing, like, these are all coming from a bunch of different degree 2 coverings. But the point is this gives us a whole lot of potential to apply abelian Chabot-T. And so this idea here is about making this explicit. So the particular approach that I took uses Kummer surfaces. So Brown and Stoll gave an explicit description of two-cover descent for hyperelliptic curves in general. What I did is a slightly different than their approach, though it's in spirit the same basic idea. So what I did is using, so first off, my approach is limited to genus 2 quintic curves, largely for some reasons of practicality. There are some reasons why the case where you don't have a rational Weierstrass point is just a lot harder computationally. So the Kummer surface of the Jacobian is the K3 surface that you get by blowing, you quotient by the -1 map. And then this gives you 16 nodes coming from the 2 torsion points. And then you blow up at those, you get this K3 surface. That's the Kummer surface. Flint, Hast, and Van Leeuwenhoek gave explicit equations for both this and also its twists, in a sense that I'm not going to define precisely, but they're the sort of twists that we need for descent. And so these are the models in which we're going to be embedding the curves that we use descent on. And so the image in the Kummer variety, this is a smooth genus 5 curve, so a lot more tractable than genus 17, which is canonically embedded by a hyperplane section, which in my paper I give an explicit equation for. in P5, where this surface exists as a complete intersection of 3 quadrics. And so we sort of have a diagram showing this picture here, where on the left you've got these different curves. So this is the genus 17, genus 5. Here's the original curve. Here's like the base P1. And these are embedded in the surfaces on the right. And so one of the tasks in my paper is computing explicit formulas for the left diagram, as well as the branch locus of this map here down to P1. And in addition, now let's bring those elliptic curves into play, not just over Q bar, but over an explicit number field. So we take another root of this quintic polynomial f, and over the number field where that's defined, we can define this elliptic curve, and there's this quartic form involved in defining it. I'm not going to write the equations here, but it's given by an explicit formula in the paper, and also all implemented in Sage and Magma. And this gives a factorization of this map from the previous slide, where now this factors through it, like maps down to an elliptic curve and then down to P1 through this explicit map here. So this is exactly the data we need to apply elliptic Chabot to this genus 5 curve. And we also get a nice description of the Jacobian. In fact, the Jacobian of this genus 5 curve is isogenous via an explicit isogeny to the restriction of scalars from this number field, which generically is quintic, down to Q, of the restriction of scalars of this elliptic curve. And there's also a version for when f is irreducible, or is reducible. I just left the statement out here to make it simpler, but it's very similar to this. And so then I implemented all this in Magma. And so here's what the algorithm does. So first we compute all the constructions that I just discussed. And then we search for rational points. If we don't find any, we check if it's locally solvable. And if so, well, I haven't implemented the right version of the Mordell-Evasive yet. So right now, if that happens, we have to give up. But at some point in the future, once we have the Mordell-Evasive, we could use that to show that there aren't rational points. And then we attempt to compute generators for the Mordell-Evasive group of this elliptic curve. In practice, this does require assuming GRH to make it feasible. There's some class group that you need better bounds for in order to make computing it feasible. And then we run elliptic Chabot to compute rational points on these curves and pull back the resulting points on all these z deltas to obtain the set of rational points on the curve. So then in terms of the results, so Boston University has this thing called the Shared Computing Cluster. It is a roughly 28,000 core Linux cluster, just a distributed computing cluster. I ran this for all 7,700 roughly genus 2 quintic curves in the LMFDB of rank greater than or equal to 2, which means rank 2 or 3. And here was the outcome. So about 13.6% of the time, it just worked. Some of the time, there was this apparent failure of the Hast principle, where it looks like a twist has rational points, or has no rational points, but we can't prove it. Some of the time, a Mordell-Evasive rank of one of these genus 5 curves was too high. Like if it's rank 5, and this curve is genus 5, well, we're out of luck. Sometimes we weren't able to compute the Mordell-Evasive group. You know, Magma can't always compute it exactly. And sometimes it just kept running long enough that, well, I set a cutoff time past which we wouldn't keep trying to compute. And for each of these, there's detailed data recorded to allow reconstruction of the results and records what went wrong if something went wrong. The successful results will be incorporated into the LMFDB soon. And just to give you a sense of how long it took, where the method succeeded, the median runtime was, 529 seconds. It's sort of in a long tail distribution. Didn't seem to significantly increase with the discriminant. And a big thing that would improve the success rate here is if there was an improvement to descent algorithms for elliptic curves, like implementing 3 or 4 descent over number fields. So here's the links. You can check out the preprint, which will appear in Algorithmic Number Theory Symposium proceedings later this year. And you can also see the code and the raw data on GitHub. So I will stop there.